The European Particle Center, examining CERN, reveals information about a brand new particle accelerator. It is twice as big as before and twice as deep, discovering 3 new particles that may assist us in comprehending the origin of the universe and its future development. CERN researchers recently published results that alter how we see the universe below the surface. There is a universe of new ideas ahead, experiments involving strange particles and forces that could belong in a science fiction film. These discoveries may open potential points of entry into other dimensions and substances that challenge the very foundation of what mysteries actually exist. Let's explore these tests, explore the environment of CERN and the facts that have the power to change our world. The entrance to wormholes and new dimensions could theoretically occur out of the blue, possibly in the sky. One explanation may be the revolutionary experiments carried out at the Large Hadron Collider, LHC, at CERN. The LHC, or Large Hadron Collider, is the largest and most powerful particle accelerator in the world, located near Geneva, crossing the French and Swiss borders. It probes mysteries regarding the peculiar organization of the world and secrets that may alter our understanding of physics and the cosmos. CERN, the European Nuclear Research Organization, operates this enormous scientific instrument, which spans over 27 kilometers and sits far below the Earth's surface. Its primary function is to allow physicists to study large hadrons and evaluate claims proposed by various particle physics theories, such as the Standard Model. The LHC accelerates protons to nearly the speed of light before smashing them together. These collisions produce a shower of new particles that researchers study to learn more about the fundamental laws of nature. One such particle, the Higgs boson, often referred to as the God particle, was discovered in 2012, helping us understand how particles acquire mass, a crucial concept in particle physics. The LHC conducts experiments essential to understanding conditions that resemble those just after the Big Bang. The data gathered may help us understand the origin of the cosmos and reveal the essential elements of matter. The LHC might uncover new dimensions of reality that could illuminate the mysteries of dark matter and the fundamental elements of nature. Some concerns have been expressed about high-energy tests at CERN, suggesting they might result in micro-black holes or strange matter that could threaten Earth. However, CERN ensures all necessary safety precautions are taken. The scientific community closely monitors all experiments, verifying through theoretical frameworks that any risky scenarios are extremely unlikely. CERN's ongoing research continues to expand our understanding of the universe, showcasing human creativity and global cooperation in our collective quest for knowledge. Not only is the LHC a technological marvel, it is also a modern engineering wonder. The LHC lies in a 27 kilometers tunnel beneath Switzerland, reaching a maximum depth of 175 meters, making it the world's largest underground particle collider. Its structure includes a 3.8-meter diameter tunnel with 2 adjacent pipes for guiding protons moving in opposite directions at nearly light speed. These paths are maintained by a series of superconducting magnets, cooled below space temperatures using advanced cryogenic systems. The collider includes 1,232 dipole magnets and 392 quadrupole magnets, focusing and guiding proton beams. Each magnet weighs 35 tons and stretches 15 meters in length. The LHC's primary goal is to investigate the fundamental nature of the universe by analyzing the smallest components of matter. By accelerating and colliding particles, physicists can observe how particles behave, how they gain mass through the Higgs field, and investigate antimatter, dark matter, and fundamental natural forces. One of the LHC's greatest achievements was the 2012 discovery of the Higgs boson, confirming theories about how particles acquire mass. In addition to the Higgs, the LHC has discovered exotic particles like tetraquarks and pentaquarks, expanding our understanding of hadronic matter, which forms atomic nuclei. The LHC encourages international collaboration, bringing together scientists from over 100 nations. This global scientific partnership highlights the importance of cooperation in solving the most pressing questions in physics. The LHC acts like a magnifying glass into the quantum realm, allowing scientists to probe essential components of particle acceleration and collision. It operates through beams of protons or heavy ions traveling in vacuum tubes, encased by superconducting electromagnets cooled below space temperature. These beams are directed to collision points, where they replicate conditions immediately after the Big Bang, generating numerous subatomic particles. The LHC includes 4 major detectors. 1. ATLAS, a general-purpose detector. 2. CMS, similar to ATLAS but with different design. 3. ALICE, focuses on heavy ion collisions. 4. LHCb, studies differences between matter and antimatter. These detectors record particle mass, charge, and momentum, helping physicists test theoretical predictions and search for new particles and forces. Beyond the Higgs boson, the LHC has uncovered previously unknown particles like pentaquarks and tetraquarks, improving our understanding of the strong nuclear force that holds atomic nuclei together. Some theoretical risks have been proposed, such as micro-black holes or strangelets, hypothetical forms of matter. But extensive studies show these risks are extremely improbable. Black holes generated in the LHC would evaporate immediately via Hawking radiation, posing no danger. Cosmic rays, which naturally strike Earth with far greater energy than LHC collisions, have never produced such events, further proving that these fears are unfounded. CERN conducts thorough safety assessments, supported by international research, and ensures all experiments are under strict oversight. While science fiction sometimes exaggerates theoretical risks, real-world science confirms the LHC is safe and invaluable in our quest for knowledge. Among the most fascinating experiments are those searching for magnetic monopoles, hypothetical particles with a single magnetic pole. Unlike common magnets with both a north and south pole, monopoles could explain why electric charge is quantized. Although magnetic monopoles have not yet been observed, their discovery would revolutionize our understanding of magnetic fields and could enable new technologies in energy transmission and storage. Furthermore, detecting monopoles would provide experimental support for grand unified theories and string theory, both of which aim to unify all fundamental forces of nature within a single framework. How scientific curiosity pushes boundaries that once belonged to myth or fiction. The idea that magnetic monopoles might exist has long fascinated physicists because it would not only revolutionize our understanding of electromagnetism, but also bridge gaps between quantum mechanics and general relativity. Their detection at the LHC would be a monumental step toward a unified theory of everything, a dream that has eluded scientists for decades. The search for such particles, along with the continuing exploration of dark matter, supersymmetry, and extra dimensions, makes CERN not just a facility but a beacon of intellectual ambition. Its work is at the cutting edge of science, probing energies and forces that mimic conditions less than a billionth of a second after the Big Bang. CERN's importance also lies in its global collaboration. Over 10,000 scientists from more than 100 countries work together, representing not just a shared pursuit of knowledge, but a rare model of peaceful international cooperation. These scientists rely not only on physical experiments, but on massive computational infrastructure, artificial intelligence, and machine learning to analyze and interpret the data generated by the LHC's collisions, billions of particle interactions occurring each second. Even as the Large Hadron Collider continues to yield remarkable insights, CERN is already planning its successor, the Future Circular Collider, FCC, envisioned to be nearly 4 times longer than the LHC and capable of reaching even higher energies. If realized, the FCC could further unravel mysteries such as the nature of gravity at quantum scales, or perhaps even provide the first observational evidence of multiverse theories. As we venture deeper into the structure of reality, uncovering layers of matter, force, and symmetry, it becomes clear that each answer leads to even more profound questions. From the enigmatic behaviors of subatomic particles to the possibility of parallel dimensions, CERN's work continually redefines the frontiers of human understanding. In a world often divided by borders and ideologies, the search for fundamental truth at CERN stands as a powerful symbol of unity through science, a reminder that the greatest discoveries are those that connect us, not just to knowledge, but to one another. The adventurous passion and curiosity that inspire scientific inquiry and investigation at CERN reveal the potential for exceeding the speed of light with particles. Another out-of-the-ordinary LHC experiment involves exploring the possible presence of particles that could potentially move faster than light. According to Einstein's theory of relativity, the speed of light is the maximum speed in space and time. Despite this, some theoretical frameworks suggest the existence of fictitious particles, tachyons, that always travel faster than light. If discovered, a tachyon would essentially challenge our understanding of causation and spacetime. Although most physicists remain skeptical of tachyons' existence, the quest for such particles at the LHC demonstrates its willingness to explore even the most theoretical aspects of physics. The LHC's ability to recreate early universe conditions enables scientists to replicate the circumstances present in the first moments following the Big Bang. High-energy collisions at the LHC bring quarks into a state of matter known as quark-gluon plasma, which existed only milliseconds after the initial explosion. The goal of plasma physicists is to understand how the universe evolved from its initial high-energy state into the organized cosmos we observe today. For example, CERN experiments with quarks and the production of magnetic monopoles in gluon plasma highlight the range and ambition of its scientific endeavors. The Large Hadron Collider, LHC, is crucial to contemporary physics, pushing the boundaries of human knowledge through particle collisions at unprecedented energy levels. These collisions allow scientists to study the fundamental characteristics of matter and the forces that govern the universe. The persistent pursuit of the unknown reflects humanity's natural curiosity and desire for discovery. Findings at the LHC have broad implications for our understanding of the universe's origin, evolution, and ultimate fate. Moreover, technological developments from LHC studies have practical applications beyond particle physics, contributing to advancements in materials science, information technology, and medical diagnostics. The LHC also fosters global cooperation, inspiring a new generation of scientists. Researchers from all over the world collaborate, exchanging knowledge and skills to uncover the universe's mysteries. This international partnership underscores science's unique ability to transcend borders and unite people for a shared purpose. In conclusion, the Large Hadron Collider is essential to modern physics. It enhances our understanding of fundamental particles and forces and provides invaluable insights into the early stages of matter. Through technological innovation and international collaboration, the LHC exemplifies the spirit of scientific inquiry and the boundless possibilities of human exploration. As we continue to study the universe, the LHC brings us closer to answering some of the most profound questions about existence and the cosmos. The LHC has already produced groundbreaking discoveries, such as the verification of the Higgs boson in 2012. But more research is planned. CERN is preparing several upgrades and initiatives, including the High Luminosity Large Hadron Collider, HLLHC, the next major improvement. Set to begin operations in the late 2020s, its primary goal is to significantly increase luminosity, the number of collisions per second, allowing researchers to examine rare phenomena in greater detail. Key upgrades include stronger magnets to better focus and steer particle beams, new superconducting technologies to boost energy efficiency, and advanced detectors for more precise measurements of particle interactions. These enhancements will help physicists study the Higgs boson more accurately, search for new particles, and deepen our understanding of the forces shaping the universe. Beyond the HLLHC, CERN is exploring the Future Circular Collider, FCC, a next-generation accelerator that could span 100 kilometers in diameter, 4 times the size of the current LHC. The FCC would collide electrons and positrons to create an exceptionally pure source of high-energy bosons for research. It could help scientists investigate dark matter, explore physics beyond the standard model, and study supersymmetry and extra dimensions. If approved, construction of the FCC may begin in the 2040s, marking the next phase in our effort to unlock the secrets of the cosmos. Among the greatest cosmic mysteries is dark matter and dark energy. While ordinary matter makes up just 5% of the universe, dark matter accounts for about 27%, and dark energy, the force driving the universe's accelerating expansion, comprises the remaining 68%. Dark matter's existence is inferred from its gravitational effects on galaxies and large-scale structures, even though it cannot be directly observed. Scientists believe it may consist of weakly interacting massive particles, WIMPs, or actions, which the LHC is currently investigating. The LHC plays a vital role in dark matter research by identifying missing energy in proton collisions. If dark matter particles are produced, they may escape detection but leave behind unbalanced energy patterns. Researchers are also studying how exotic particles might interact with dark matter or be linked to the Higgs boson. Dark energy remains even more elusive. Some theories propose it is related to quantum fields or potential modifications to Einstein's theory of gravity. Although the LHC cannot directly detect dark energy, certain experiments involving the Higgs boson may offer clues about its role in the larger cosmic framework. Future accelerators like the FCC will continue advancing our understanding of these enigmatic components of the universe. These efforts bring us closer to solving some of the most important and profound problems in physics. The search for answers at CERN is not limited to particles alone. The LHC's infrastructure supports a multidisciplinary approach, allowing physicists, engineers, data scientists, and computer experts to collaborate on solving problems that stretch across fields. This integrated model of research fosters innovation at the intersection of theory and technology. One striking example is the development of the Worldwide LHC Computing Grid, WLCG. It was created to process the massive amounts of data generated by LHC experiments, over 30 petabytes per year. This global network of data centers is a testament to human ingenuity and international collaboration, providing unprecedented computing power to analyze complex interactions at subatomic levels. These computational advances have influenced fields far beyond physics, including medical imaging, climate modeling, and artificial intelligence. Tools and algorithms developed to interpret particle collisions have found new life in detecting tumors, optimizing logistics, and analyzing big data in real time. Moreover, CERN's spirit of openness and education extends to future generations. Programs like CERN's summer student internships and open data portals ensure that knowledge is shared widely, inspiring young scientists and enabling institutions around the world to contribute to and benefit from cutting-edge research. The scientific process at CERN is not only about outcomes but about the method and collaboration that lead there. The LHC is a modern cathedral of science, not in stone and stained glass, but in steel, superconductors, and data. It embodies a global commitment to pushing boundaries, questioning established norms, and imagining realities beyond current comprehension. As we move into the mid-21st century, the questions grow even more profound. Can we unify quantum mechanics and general relativity into a single, elegant theory of everything? Is there a multiverse beyond our observable reality? What role did symmetry and asymmetry play in shaping the matter-dominated universe we inhabit? And could our understanding of time, space, and dimension be radically incomplete? The LHC and its successors stand at the threshold of such discoveries. Every particle tracked, every collision logged, and every anomaly explored adds another piece to the cosmic puzzle. Whether or not all answers are found in our generation is secondary to the fact that humanity is bold enough to ask the questions at all. In a world often divided by borders, ideologies, and conflict, CERN remains a beacon of unity, driven by the belief that knowledge, pursued collectively, can uplift civilization. The experiments at the LHC, and those yet to come, do not just change our understanding of matter and energy, they illuminate what it means to be curious, collaborative, and human.